1, 2, 3, test. Okay. Yeah, so today, because we have our quiz on, what was it? Wednesday, right? And then, oh yeah, by the way, remember, Wednesday, our class delayed by 1 hour. It's also the day of the quiz. And so everyone wants to study more. The quiz covers chapter 7, so I'm going to do tutorial today. And we will, yeah, so we will do the question 7. That's the hardest question, right? So I will do in a method that is different from the solution. So there's two ways. The solution, right, is the method is given by the textbook is, I believe for you guys, is not very familiar, right? It's because it's simultaneously treating force as a vector and then also need to do integration. So two difficult things at the same time. I'm going to do a different method there. But for now, let us continue talking about the energy of the harmonic oscillator, right? And after that, we start talking about the pendulum. So let's go to full screen. Okay, so if you recall, right, we pick up where we left off in the previous class. We were talking about the mass of mass m, right? And then we attach to a spring. And for now, we treat the surface as smooth. So there's the only force acting on this mass is the spring force, right? So F equals to kx. Okay, so as you can see, we are using the formula F is equal to kx, and we have learned when we were talking about potential energy last time, the integral of F is half kx squared. That gives us the potential energy. Okay, and then the minus sign tells us the direction. So if I take right as positive, is when x is a positive number, the force is to the left. If the mass is on this side, the force is to the right. So it's always opposite to the sign of x. Okay, and from here we use Newton's law. So F is equal to mass times acceleration. We have dx dt squared is equal to minus kx, and then this is the equation of a simple harmonic oscillator. So KOM times x. And from there, I have shown you how to solve this solution in the previous class. The position as a function of time is given by some constant a cos omega t plus phi 0. Okay, so phi 0 is the initial phase, and what is omega? So omega is square root of k over m, right? So Kaishan was asking, where do the constants come from? So there's two categories of constants that we are dealing with here. So the k, right, is a Hooke's constant, right? So it's a spring constant. It depends on the property of the spring. So a different spring will have different value of k, and a solid and stiff spring will have a higher value of k, right? So it depends on the nature of the spring. But these two constants here, right? So this a and phi 0 is also a constant. But this constant is depend on the situation. That means for the same spring, the A amplitude depends on the initial position. The phi is also depends on the initial position. So these two constants depend on what happened at time 0. Okay, and because it's many different possibilities, because at time 0, right, you can arrange any situation, whether the spring start from rest or the spring is already moving, right? So all these different situations will give you the different possible values of A and phi 0. Okay, so there's two different types of constant over here. Then once we've got the position here, we can calculate the velocity, because velocity is dx dt. So dx dt will give you v, and I can now express my velocity as a function of t. Just differentiate this, right? So I got negative omega a sine omega t plus phi 0. Okay, so this part is pretty easy. Then in the previous class, I have shown you how to calculate the energy. So let's go through this again. We have more time and we can go a bit slower. The energy is given by E is equals to K plus U, right? So K plus U. What is K plus U? It is the K is kinetic energy, so half mv squared. U is potential energy, so half kx squared. Right, so now I have these two expressions. I can substitute inside, because my v can go into here, my x position can go into here, right? So I can put these two things inside, and then let's see what we get. So I got half mv squared, so I got half m and then the square of velocity. So omega square a square sine square omega t plus phi 0. And then half kx squared, so half k, and then I square the x, so it's just a square cos square omega t plus phi 0, right? Then we can try to simplify further, because as you can see, right, over here got omega square. Omega is given by this expression, so I can put it here as well. Okay, so I can put this here, so I got half m k over m a square sine square omega t plus phi 0, and then plus half k a square cos square omega t plus phi 0. Okay, so I can cancel the m. Then after cancelling the m, we recognize that everybody has a factor of half ka square. So half ka square, so I can take it out. Okay, so what's left inside is sine square omega t plus phi 0, and then cos square omega t plus phi 0. So I suppose everyone knows by now, sine square plus cosine square, the whole thing is just equals to 1. Therefore, my energy of my harmonic oscillator is half ka square. Okay. Half ka square is energy, yes. Yeah, so it's the total energy. So energy of the system. So energy of the system, remember, is kinetic plus potential. All the energy, mechanical energy, right? So this is mechanical energy. Mechanical energy means kinetic plus potential. Okay, so as we can see here, right, the energy depends on the k and the amplitude. So if you have a spring, right, because a spring, the amplitude depends on the initial conditions. So correct, right? Yeah, half ka squared is energy. It depends on the initial condition. So the amplitude is, how do we get the different amplitude? It's very easy to imagine, right? So you have a block, right? So if you don't do anything, the spring is not moving. But if I shift the block and then I let go, it will become the amplitude, right? So if I shift it by 5 centimeter and let go, the amplitude will become 5 centimeter. But if I pull further 10 centimeter, pull by 10 centimeter and then I let go, the amplitude will become 10 centimeters. So depends on how much you stretch the spring and then you let go, that becomes the amplitude. Okay, you can also start the spring not from rest, right? You start the spring from the middle and then you kick the spring. So you, instead of an initial position starting from rest, you give it an initial velocity, you kick the spring and then you start to move. So you got the energy, and this amount of energy will determine the maximum amplitude as well. And also, of course, the k, depending on how strong the spring is, it can carry more energy or less energy. Yeah, correct. So if you remember what we did in chapter, was it chapter 3? Yeah, we integrate the kx dx, it will give you potential energy, right? So and this is, yeah, so it's these two things sum up together, and after we simplify, we get half ka squared. So that is the energy of the system. Okay, so that is the energy. Quite a important situation, so let me remember this, right? Let's go back to express the kinetic energy. So what was the kinetic energy? Okay, so let's check the kinetic energy again. Okay, so the kinetic energy is half ka. Okay, so yeah, go a bit slower, right? So kinetic energy is, let me slow down a bit, is half mv squared, right? So half mv squared. So what is v squared? I have shown you that v squared is given by this, so I got omega squared a squared sine squared omega t plus phi 0, and then I have also used the formula that omega squared is equals to k over m. So I put this inside, right? So k over m, it will cancel with this m, so I got half ka squared sine squared omega t plus phi 0. Okay, so I'm just repeating, but I'm focusing on kinetic energy now. Why, you will see later, but for now, right, let me use the trigonometric identity. So this is sine square. Okay, so sine square, right, I can express as 1 minus cos square, again using trigonometric identity. Okay, so I got this, and let's see what happens if I put the a square inside. So I got half k, and then I got a square minus a square cos square omega t plus phi 0. Okay, so do you recognize what this is? So this is actually just the position, right? It's just a position square, so it's just the square of x. So this whole thing is x squared. Okay, so from here we conclude that, next page. So from here we conclude that my kinetic energy is half k and then a square minus x square. Okay, so I got this expression, right? So this is another way to express kinetic energy. But why do I do it in this way? Because I want to show you something. For one thing, right, kinetic energy is supposed to be half mv squared. M is mass, is positive number. V square also is a square of something, right? So it must be positive number. So kinetic energy must be positive. Okay, so kinetic energy must be positive. Then look at what happens on the right hand side. It is a minus something. Okay, so the value of x, right, must not make kinetic energy negative, otherwise it doesn't make sense. So that means this number must be smaller than this number. Okay, so therefore I conclude that the magnitude of x must be smaller than the amplitude. Okay, so this is the allowed domain of x. So that means the allowed domain of the position of the spring. So by analyzing the kinetic energy, we are able to say what is where is the box allowed to be, right? So if any position greater than a, cannot be, so the box cannot exist there, right? So that that tells us how to determine the domain of x. Okay, so any questions so far? Too many trigonometry. It's only sine and cosine, so yeah, total minus potential positive, correct. That's what we are doing. But x here is not a vector. X is the x coordinate. X coordinate. Yeah, so x can be exactly equal to a. So if it's equal to a, then it just means k0. So 0 kinetic energy is fine. That means the box is velocity is 0, right? So 0 kinetic energy means 0 velocity. Okay. Yeah. Any other question? Yeah. So now let's explore a little bit further. Let's draw the graph and see how it looks like. So let's draw the graph of all the energies for different positions. So my horizontal axis now is the x coordinate. Okay, so yeah, x is not a vector, but it's the x direction, so it's the x coordinate. And from here we conclude that the allowed domain is from minus a to positive a, maybe something like that, right? So minus a to positive a. So the position of the x can be anywhere between here to here, but not outside, right? So this is the origin, so this is x equals to 0. X equal to 0 means is the equilibrium position of the spring, right, on the box on the spring. Okay, so the total energy is some number here, and by conservation of energy, the total energy we expect it to be constant, so it's a horizontal line like this. And then let me draw nicer. Okay, so this is the total energy. So this position is the E, right? So this is the energy axis. So the E here is half Ka square. This is the total energy, right? And let's look at the potential energy. So the potential energy is half Kx squared. So it's a quadratic graph. So the quadratic graph is like this, right? So we only need to draw from negative a to a. Okay, so half kx squared is my potential energy. So when x is equals to a, it's just half ka squared. So half ka squared is the same as this, right? So this is the point where the potential energy is the same as total energy. So this is a quadratic graph, and then on this side also is the same. And then when x is 0, the energy here, the potential is 0, so it will pass through 0 here. So I got a quadratic graph like this. Right? And then the kinetic energy is a negative x squared. So it's negative x squared, so it's the upside down quadratic graph. But when x is equals to a, right? When x is equals to a, the kinetic energy is 0, like what you are asking just now. So when x is equals to a, this is the kinetic energy, is going to be 0. When x is 0, the kinetic energy is half ka squared. So when x is 0, the kinetic energy is half ka squared. Right? So this is also a quadratic graph, so I'm going to draw it like this. Yeah, I'm trying to make it look nice, so I got this. Okay, so this graph is k is half k a square minus x square, and this graph is my potential energy graph. So u is equals to half kx squared, right? And of course, my total energy is k plus u. So k plus u, this value plus this value always add up to this, right? So at every point, so the total energy is the same, okay, for different positions, right? So as you can see, right, the potential energy is always the opposite of the kinetic energy. So at the endpoints, right, when the potential energy is the highest, is equals to the total energy, the kinetic energy must be 0, right? So this point is the 0 velocity. So at the furthest distance, the spring will become 0 velocity, right? But then if I come here lower and lower, right? So if I come here lower and lower potential, so my kinetic energy is higher. So as I go away from the maximum distance, around near the center region, the velocity is very high. So that is where the spring is moving the fastest, right? So the kinetic energy is the highest, the potential is the lowest, right? Then continue going on some more, the potential come up again, so the speed will decrease again until we reach on this maximum point. Then the velocity at this point must be 0. Okay, so the spring, this is how the spring will oscillate between the two. The maximum distance is near the center, right? And then the end points is where the velocity is 0. Okay, so yeah, so let's say something here. So the velocity is high over here. So in this region, the velocity is high, and then here is velocity 0. So here is velocity 0. Okay, so that is the potential energy and kinetic energy of the spring. Any question? Yeah, so it's like a vector in one direction, only has x coordinate. So x should be 0, x0 should be Vmax, correct? And then when x is AV is 0, yes, correct. So the acceleration is 0, yes, yeah. How to get the graph? The graph is just plot the graph of math. Half kx squared is a half kx squared is the potential energy. So I'm just plotting a quadratic graph, right? So plotting a quadratic graph, and then kinetic energy I have calculated to be ka squared minus x squared. So it's a quadratic graph where the leading coefficient is negative, so it's upside down. So it's got this, and then we figure out the points by substitution, right? So when x is 0, what is the point? When x is plus or minus a, the k is 0. So just join the graph, right? So I believe in calculus there's a lot of questions about plotting graph. There's more, but I'm just doing it the simple way. Okay, so I got this situation. Then yeah, because partly the reason why, right, with a coefficient, yes, we just need to look at this equation, right? So my kinetic energy has sine square. My potential energy has cos square. So, and then sine square plus cos square equals to 1 with the coefficient. So exactly like you said. Okay? Yeah, so about the acceleration, right? For the acceleration, we remember the equation. So F is equals to minus kx, right? So the mass times acceleration is negative kx. So when x is 0, the acceleration is 0. But even though acceleration is 0, but this is the situation where the velocity is highest. Okay? And also, right, yeah, the velocity is highest. So it's still moving, right? But after that, it will slow down. Okay? So this is where the acceleration is highest, and then when the velocity is 0, the acceleration magnitude is also the highest. Right? Okay, any other question? So usually for a conserved quantity, right, the energy is k plus u, right? And if it's constant, so energy is constant, then we just need to look at k plus u. And the condition that k must be a positive number, it will determine the domain where the x can move. So for the case of the spring, x is less than a. Okay, so that is quite important over here, right? So yeah, never mind. I wanted to say something about quantum mechanics, but quantum mechanics, something strange will happen that will violate this thing. If you know what I'm talking about, you probably know what I'm talking about. But if you don't know, then never mind, right? We will, because that is a future course. But that's very interesting. I'm talking about quantum tunneling. Okay, so yeah, so the potential will determine the motion of the particle for conserved systems. What is your question? Because this is just Newton's second law, right? Yeah, because some of you have read up about quantum mechanics. Yeah, like what is your question? Which is the highest A? So m and k are constants. M and k are constants. So if x is high, A is high, right? Because A is minus k over mx. So if x is 0, A is 0. Right? If x is a, then if x is capital A, then acceleration is the highest. Okay. I forgot to open the lecture notes. So we will talk about the example. So let me open the notes. The energy. Yeah, so basically I'm just like talking about everything about this picture, basically, right? Any other question? Okay, so let's look at the example 8.3.1. So we have a spring okay, so I have a spring that is mounted horizontally, and then its left end is fixed. A spring balance attached to the free end towards the right, given by this, indicates that the stretching force is proportional to the displacement, and 6 Newton causes 0.03 meters. So this whole thing, right, is just teaching. This is just providing us information on how to calculate the k, the spring constant. Okay, and then so we got the K already. Then you replace the spring with a glider. So the mass is 0.5 kg. You pull it to this value and then you release it from rest. So the first thing to do is to find the spring constant. Okay, so yeah, let's find the spring constant. So according to the information given, right? So the information given is, well, let's talk about the magnitude, right? So the magnitude of F is the magnitude of kx. Because I don't want to confuse myself with the negative sign, it's just telling us that if I stretch by 6 newtons, the magnitude of displacement is 0.03 meters. So from here I can calculate the K is equals to 200 newtons per meter. Okay, so this is my K. Okay, so the next thing I want to do is just to find the omega, F, and the period. So this one is just substituting in formula. So the angular frequency is given by K over M, right? So K is 200 Newton per meter. The M is 0.5 kg. So if you calculate everything, it's a square root of 400. So it's 20 radians per second. Okay, and then from omega, we can easily get frequency because omega is equals to 2 pi F. So therefore my F is just omega over 2 pi. So it's 20 over 2 pi. So if you divide, you get 3.18 hertz. Okay, and then the period is 1 over F. So it's 1 over 3.18. So it's 0.314 seconds. So this is the period. Okay, and then find the total energy of the system. So the total energy of the system is half Ka square, right? And then so the how to get the amplitude. Yeah, so the amplitude, right, it says that I pull it to 0.2 meters and release from rest. So pull to 0.020 meters, then release from rest. So this means the amplitude is this number, 0.02 meters. Okay, so from here I can now calculate my energy. So half K is 200 and then 0.02 square. So if you calculate everything, you just get 0.04 joules. Okay, so this one is a pretty simple question. Yeah, just the magnitude. Yeah. Yeah, so happen to be pi. Is it because at some point we divided? Yeah, I think the number pop up because of this. And then the other quantities, maybe it cancel each other. Or maybe it's just a coincidence. 0.1 pi. Okay, so everyone clear? Charles, are you clear with the highest A? Okay, clear? Okay, okay. So yeah, so that's the energy of the how do you calculate the energy of the harmonic oscillator? Okay, so question 3, page 3. Yeah, that's true. We divided the integer with 2 because the frequency all are like exact number 200. The K is 200. The omega is 20. So it come out with a pi. Okay, so yeah, before I started the class, right, I don't know how many people have seen the video because that was before people joined, right? I was showing a video where you can measure the acceleration of gravity using hair. So maybe in the break time I'll show the video again for those who came in later. I have also put the video in the OneDrive, so you can get it from there also. Okay, or for the break, do you prefer to see the other videos about the Einstein thesis? I watched also. I find it quite interesting. Started to get interested in it already. Okay. Any question? Long hair or short hair? Well, she has she has super long hair, right, until her waist. So definitely my hair cannot measure G now. Okay. So so now we want to talk about another oscillating system. Previously, we have spent time talking about the mass attached to a spring vibrating. Another oscillating system, right? We are talking about periodic motion. Oscillating system is a periodic motion. So another type of repeating motion is the pendulum, right? So pendulum is usually we talk about a mass m, okay, and then it is suspended from a string of length L. Okay, and just like what she said in the video, right? We neglect the mass. So that means usually we take a very thin string, so the mass is negligible. So it's negligible mass. So all the mass is here. Okay, so so what we're talking about is a pendulum. So I have something attached to a ceiling, right? And then this is the vertical direction, and then I have a string, and then I have a mass m. Okay, and then this is the angular displacement of the pendulum. So if you let go of the pendulum, it's just going to swing back and forth, right? So this is the simple pendulum. You want to get long hair? Yeah, because MCO, the quarantine will make everyone have long hair. In the first quarantine, right, my hair was super long. You haven't met me yet at that time. So the March to when March to May or June, the quarantine period, my hair was super long. Yeah, actually true. Now can already lah. Yeah, now can already. So let's try to solve this motion. I have a mass m and then hanging from a ceiling of mass L. Okay, I'm going to do an approximation. So if it's swinging, right, then it's moving at a part of a circle. So this is kind of like a circular motion, right? But we want to focus on the horizontal displacement only. But first, let us draw the free body diagram. So what is the forces acting on the object? So we have done this many times already, right? So I got the weight mg, and then I got the tension along the string. So this is a T. Okay, and then I want to resolve the components of mg. So I want to resolve it to two directions. Firstly is the direction that is tangential to the motion, and the second direction is this way, right? So from here I got mg cos theta, and then I got mg sin theta. Okay, so I will resolve this. Okay, and then I'm going to do an approximation because the full equation, right, cannot be solved. So so now, right, we consider the case where theta is small. Okay, so when theta is small, right, then my pendulum is almost vertical. Right, and then this component, right, so the component, the tangential force direction is approximately horizontal. Okay, so this is my tangential component. Okay, so it is almost horizontal, approximately horizontal. Okay, so everyone agree, right? No objection, because if the theta is small, right, almost vertical, then the tangential component is tangent to the circle, right? So tangent to the circle, so near the horizontal direction it is mostly horizontal. Okay, if it's approximately horizontal, then I will take the coordinate system to be my x and y here, and then my origin here. Okay, so take the coordinate system. Where origin is where m theta is equals to 0, so I choose this as my origin, right? And then I take right as positive. Okay, then the horizontal force is well, Fx is equals to ma in the x direction, right? So we got this situation now. When theta less than 5 degree, why wasted money? You mean the haircut, is it? Yeah, so okay, so I'm gonna explain this. Yes, something about the Taylor series. 5 degrees, 5 degrees is how many radians? Yeah, 5 degrees should be quite small enough. Okay, so so Kaheng said something about Taylor series, and we will see this happen later. Okay, so as you can see, right, my force is acting, if I draw it this way, my force is acting to the right. Okay, this is because when x is positive, the force is to the right. When x is negative, so when my pendulum is on this side, the force is to the left. So it's always opposite the direction of x. So the force is negative mg sine theta. And then acceleration is the second derivative of position. Okay, so I got this now, right? And then now we want to talk about theta small, because sine theta is the general solution, but I want to set theta small. So for theta small, right, we have the Taylor series. Actually, by the way, have you guys learned Taylor series yet? It's taught in the calculus, right? Okay, so the Taylor series is let me see if I can remember, right? We don't need the full thing, right? I'm just like revising. Okay, so it's minus 1 to the power k theta k, and then k factorial, right? So something like that. So the first term is just theta, and then second term is all the odd numbers, so 3 factorial, and then theta 5 over 5 factorial, and then theta 7 over 7 factorial, and dot dot dot. So I don't know if you learned this yet. Not in calculus 1. Oh, okay. Yeah, because I just want to show just to show you that how the relevance of calculus class to here. So in calculus you will learn about Taylor series, but actually what we use, right, because theta is small, so theta is small, and then we for this to be valid, right, is in radians. So if theta is small, then all this power is negligible. Okay, so sine theta is approximately theta. Okay, so if you don't believe, right, let's try some numbers. Okay, so let's try some numbers. Let's 5 degrees. So let's see, 5 degrees. So 5 degrees is in radians is what? So 5 degrees is 5 times pi over 180 radians. So we got 5 times pi over 180 radians. So it's 0.087. Okay, so then let's try sine of 5 degrees. Okay, so sine 5, 0.0871. Okay, so it's pretty close, right? So the error, yeah, so the error starts to come in from here on. Okay, so this is why sine theta is equal to theta, but must be in radians. Oh, in your calculus quiz. Yes, Taylor's theorem. So the part that you do not include is the remainder. So yes, so you will learn this in the Taylor series. Yeah. So this is the error lah. So basically, I'm just taking the Taylor polynomial of one term, right? So Taylor polynomial of one term. So everything else that you do not take is the remainder. So it's R. So I only take one term, so it's just R1. Right? So this is the Taylor polynomial of one term. Okay. So yeah. So this means summation. So the Riemann sum is a summation. That's why you will see this also. Right, so it's just summing up numbers. Okay, so this one is summing from 1 to infinity. So this is an infinite series, right? But actually we only need the first term, because any small number to the power 3, right, it will be even smaller. So if you take this number to the power 3, it's like super small, right? So even smaller. The next term is power 5. It's even a small number. So we can neglect all these terms. Okay, so this is why we have sine theta. So sine theta is small. Okay, so if everyone agrees, right, if sine theta is small, so I'm going to put this back to my equation. So my equation 1, so let's call this equation 1. So for theta small, equation 1 is approximately, well, it becomes mg theta, right? So sine theta is about approximately like theta. So I got d2x dt squared, and actually both sides can cancel the m, so the m doesn't matter here. So we find that I have d2x dt squared is equal to minus g theta. Okay, so I got g theta, but then I have another problem. This is the differential equation for x. This is the angle. So I have different coordinates over here. Okay, so for different coordinates, but I will use another approximation. So theta is approximately x over L, right? So because for small theta, right? Okay, so S is equals to the radius times theta in radians. Okay, so for theta small, right, so this one is almost approximately like a horizontal displacement, right? So x is approximately the horizontal displacement, right? So that means I'm trying to say that r theta, L theta. Okay, so theta is equals to x over L. Do you agree with this? Small enough to fit the range of error. Yeah, correct. That's how. We can yes. So that's what we do all the time. Correct. Exactly. If x is small, I can replace sine x with x. Yeah. So for those who are who heard my talk on Friday, right? 2 weeks ago, was it? Yeah, 2 Fridays ago, I was giving a talk about the research talk, right? And basically the whole talk, you see the complicated math, right? Actually, it's just doing something like this only. It's actually very simple. Yeah, so it's expanding the series to simplify the equation. And physics, as you can see, in physics, we do that all the time. Because in physics, the equation is extremely complicated. So either you use computer to solve the equation, or you do things like this. Yeah, kind of, yeah, because the only reason is because we have to practice a lot. And in math, right, math will focus on slightly different areas. So math is about the concept and theorem. That one physics people is very bad at it, like me, right? So that's the difficult part. But if everyone is agreeing with this, so finally I substitute this. So I got the equation that appears like this, right? So I got theta, so it's x over L. So I got g over L times x. Okay, so this one, so this is, compare this with the simple harmonic equation. Right, so for the simple harmonic equation, right, my x of t, as I shown you in the previous class, is omega t plus phi 0. So this will satisfy the differential equation dx dt square is equals to negative omega square x. So if I compare these two, right, this is my omega, right? So so we conclude that omega square is equals to g over L, like this. Okay, so what is omega square? Hang on. Omega is this, right? So omega square is 2 pi over t is equals to g over L. So the t is equals to 2 pi L over g. So we have derived this equation. We have found that my pendulum, right? My pendulum obeys this equation. And this is the equation for a simple harmonic motion. So simple harmonic motion is given by this angular frequency. So if I compare the two, right, I conclude that period is this. So the conclusion is the pendulum will oscillate with a period given by this, right? So pendulum oscillates as a simple harmonic oscillation with period t is equals to 2 pi L over g. Wow, now everyone complaining about math. Math is Yeah, I mean, well, I agree. Is math is hard for me too. Yes. Yeah, that's right. In physics, we just spend our time calculating and calculating. Okay. So yeah, so but important thing to remember, right? So this equation is valid as for theta small, because our whole assumption is theta small, right? We get all this equation because theta is small. Okay. Any question? Thousand. Shouldn't be taking physics. Well, I don't know. Well, I mean, physics and math are still quite close enough that, you know, if you are taking math, you can still do physics, like the MAT students now. Or if you're taking physics, if you're taking physics, you're still taking a lot of math courses anyway. Is it? What was your joke? Oh, math people crying in the toilet. Okay, so now is 10:50. But basically that's our topic, right? I can't, yeah, because now it's too late to start a new topic. It's another long story. The paper. So let us take a break. Okay. Yeah, let's take a 10-minute break, and then we continue with the gravity tutorials. Okay. So yeah, let me stop the recording and then I show the paper. Yeah, so time to start. Yes, it will affect. So on Wednesday class, we will talk about the what was it? The solid pendulum. So we will consider the mass distribution. So what if it's not a string but you have a rod, right? Yeah, so that is the Cambridge. It's called the Cambridge Part 3. Tripos. So that is the graduate school. Because it's like the semester is something like 1 year, 1 year long type of thing. I don't know whether it's still like that now, but probably it is. Cambridge is a very old university, very traditional, so the using natural frequency. Oh, yeah. Yes, so if you I think for certain UK university, you get this, right? Yeah, so it's when this is small. Yeah. Yeah, the natural frequency. So if you walk, right, like her also, if you walk, the hair will also vibrate up to natural frequency. Oh yeah, so you don't cut hair for 3 more years, then maybe you can do something like this, right? Yeah, let's open the tutorial. Oh. Okay, so let's do. I think let's go straight to do the final question first before we run out of time, and then in case we run out of time, and then later we do the other questions, right? Because the last question is what you really want to do, right? So let's look at the final question first of tutorial 7. Okay, so this is a difficult question, right? I have a mass m that is distributed uniformly along a line of length 2L. So am I recording? Yes. Am I recording? Yes. Yeah. Okay. So yeah, so basically the question goes like this. So I can just immediately draw, right? So we are doing tutorial 7, question number what? Number 9. Okay, so tutorial 7, and then we're doing question 9 first. Okay, so I have the rod, right? The length of the rod is 2L. Okay, so the length of the rod is 2L. So the rod is like this. Okay, so this is my x coordinate, and then this is the center, right? So this is my y coordinate, right? And then my mass m is over here. So this is negative L and positive L. So the total length is what? It is 2L, right? And then the total mass of the rod is m. Okay, so since this is a uniform rod, if this is a uniform rod, I think, yeah, because we have done this many times, right? I believe you guys are okay that the dm is just the total mass over the total length times the dx direction. Okay, so how do you find the force? Well, the force is a bit difficult. So what I want to do is I want to find the potential energy first. So in this method, I want to calculate the potential energy of this. So what is the potential energy? Potential energy at m. Okay, so what is the potential energy at m? So this is an extended body, so we need to use a integration to solve this, right? So what we do is, well, we chop this up into many sections, and then we look at one piece. Okay, so one piece, this is a small piece, so it is a small piece, it has a mass dm, right? It has a mass dm, and then the length of this piece is small length dx. Okay, and then I want to know what is the distance from here to here. Okay, so what is the distance? Because the formula to calculate potential energy, right? If the gravitating source is this piece at this distance, then the potential energy is given by g mass times this mass over the distance, right? And I have so I guess everyone should be convinced that the dm is given by this formula, so I put this inside here. So m over 2l dx divided by r, right? So I substituted this already. And what is the distance r? So let's say, right, the height here is y, okay, and this is 90 degrees, and this is the x position of this piece. So this, I'm talking about one piece first. So this piece will have the distance of y square plus x square square root. Do you agree? Right? This is du. Okay, so this is du. So from here I conclude that my du is equals to, rearrange this. Let me write one line here first. I got gm m over 2l dx, and then my distance is y squared plus x squared, so this thing plus this thing, right? So now I want to simplify. So simplify the constants, I put it in front. So I got gm small m over 2l, and then I got dx over the square root of y squared plus x squared. Okay, so this is the potential energy of one part, but the total potential energy will be the total of all the parts, right? So I need to integrate. So the total potential energy, u is the integral of all the u, so I just need to integrate this function. So all these are constant, right? So I can take it out in front, no need to integrate. Integral of dx, and then y squared plus x squared, and then square root. Okay, so the limits of integration go from minus L to L. So it's from negative L to positive L. Okay, so now the integral of this, right, you can solve it however way you want, but since we are not a calculus class, if this comes out in the exam, the integral will be given, so don't worry about it. Okay, so the antiderivative of this thing can be calculated in this way. From oh yeah, wait. Before I do that, right, I want to simplify first. Okay, I want to simplify because, right, this is integrating from minus L to L, and then this is x squared. So this part is an even function. So this is an even function. So if this is an even function, right, I don't need to integrate the whole thing. So I just need to So I just need to integrate gmm over 2l. So if this is an even function, right, I don't need to integrate everything. I just need to integrate starting from 0 to L, and then I times 2. You also learn this in your calculus, right? And this is dx over y squared plus x squared. Okay, so I can cancel the 2 like this over here, right? So now my potential energy, make it more clean. So I put this nicely from 0 to L dx over y squared plus x squared. Okay, so do you follow so far? Yes, so you learned this before, right? Yes. Okay, good. Okay, so the antiderivative of this is given by this logarithm. So it's the ln x plus y squared plus x squared. Okay. So the next thing that we need to do is just to put in the limits. Okay. So if I put in the limits, what do I get? So I got g m over l. Right. This is a logarithm. So the logarithm upper limit minus the logarithm lower limit is just the ratio of the two. Right. So if I put in the upper limit, I got l plus y squared plus l squared. And then put in 0. So put in 0, I just get square root of y squared. So it's just y. I got this. So everyone follow so far? So this is the potential energy, right? So this is the potential energy. I want to calculate the force, right? So calculate the force. If you remember, right, the force is, well, it is a vector, right? So it is a vector, is F. Okay, so it is a F, and that means it has a x component and a y component. And how do we calculate the x and y component? Remember, it is the derivative of my potential energy. Okay. So the force, right, as you can see, this F is this M is right at the center. So M is symmetrical in the x direction. Or you can say that by symmetry, the x component is 0. Right? Because there's same amount of mass on this side, same amount of mass on this side. So the net force on the horizontal direction, they will cancel out. Okay, so Fx is equal to 0. And then how about the force in the y direction? Okay, so the force in the y direction is negative differentiating u with respect to y. Oh, is it? Okay, I will. Yeah, so I will look at it after we're done. Okay. So this is the second method, right? So I found the potential energy, and then I differentiate the potential energy to get the force. So I believe this is a method that you prefer over the solution, right? But let us try to work this out. So this is differentiating this whole thing over here. So it's negative gmm over L, and then the logarithm of L plus y squared plus L squared, and then y. Okay, so the minus will cancel each other. Okay, so the minus will cancel each other. And then these are constants, so I can take it out. So I got gmm over L, and then you just need to differentiate the logarithm with respect to y. Okay, so just differentiate. This is a logarithm, so no big deal. Gmm over L. So differentiate logarithm, I flip this, so I got y over L plus y squared plus L squared. This is L. Okay, and then I differentiate by chain rule. I differentiate this thing. Right, so this one is there, so we keep it there for now. So I got gmm over L, right, and then I got y, L plus y squared plus L squared, and then differentiating this, right, so what do I get? So let's see, this is a quotient, so I shall use the quotient rule. So I got y squared, right, and then I differentiate the inside. So differentiate inside is 2y and then 2 square root y squared plus L squared, right? And then minus, differentiating y becomes 1, and then I got L plus y squared plus L squared. Okay, so this y and cancel one of the y here. I got gmm over L, and then I got 1 L plus y squared plus L squared, and then there's a 1 over y. Yes, let's put 1 over y here, and then now let's simplify this. Okay, so I got y squared over y squared plus L squared, and then minus L minus y squared plus L squared. Okay, everyone follow so far? Actually, if you don't follow, so never mind. It's just differentiating, right? So different people will do it in different directions. Okay, so open it by your browser. Oh, is it? Okay. Yeah, so everyone okay with this, right? So this then just need to simplify. So I got gmm over L. So this is 1 over y. So let me put them together here. So 1 over y L plus y squared plus L squared. And then I just need to simplify this part. So to simplify this part, I just make all the denominators the same for everybody. So this is y squared, this is minus L, y squared plus L squared, and then minus this thing. So y squared plus L squared. Okay, so as you can see, right, some cancellation will happen just nicely. Okay, so y squared and y squared will cancel, and then what I have now is negative L squared. Wait, there's no square. Is there a square? Yeah, negative L squared. Negative L squared, negative L, y squared plus L squared, square root, and then y squared plus L squared, square root, and then I can simplify even further. So this is gmm over L, this is 1 over y, L plus y squared plus L squared. Maybe you can see some things that can cancel already because I can factorize negative L out, and this becomes L plus y squared plus L squared. Right, so y squared plus L squared, square root. So this term cancel with this term. Right, and then there's one outside L left cancelling here, and then there's a negative sign. So I got negative gmm over y times this. So this is my force in the y direction. So if we do everything carefully, right, we will get the force that is negative, so it's pulling the mass downwards because the rod is down there. Okay, so I have found the force in the y direction already. Any questions so far? I know this is a messy differentiation, right? But at least we can get the answer, right? And it's just differentiation, so it just takes a long time, but it's just differentiating, right? So just slowly do, and then the nice part is like if you do everything properly, you see a nice cancellation, then everything becomes simple at the end. Yeah, I know it's quite long. So this is where, yeah, like you guys were saying, right, the physics student do calculating all the time, and the more you do it, that's why you become faster than mathematicians. Yeah, in the first way is in the solution. Yeah. What integrated will be the force? No, the integrated one is the potential energy, right? So in the previous line, we do the integration to get the potential energy, right? So potential energy is this integration, we got this. And then we differentiate the potential energy to get the force. Yeah, so if it's the force way, right, the force way you do it this way. Okay, I'll just briefly comment about it lah. Because I want to avoid doing the force way. I think it's because it's harder. And I haven't really shown you the method yet. So let's say this is the y, right? And then we look at this part. Okay, so this part has mass dm. Okay, and then the distance is still r. Okay, so r is y squared plus x squared. So let's say this is the x position, right? And the length is dx. Okay, so what is the force on m, right? So we can calculate the force on m. Due to this piece, right? So dm, right? So is well, I got the let me calculate the magnitude first, right? So the magnitude is f, right? So the magnitude is f is g m dm over r square, right? So r square, and r is this, so it's gm. Yeah, let's keep it like this first. Okay, so this is the magnitude, but then I want to calculate the components. So the components is, there's a y component and there is a x component, right? So what is the y component? So the x component is going to be 0, and then the y component is fy, right? Is the magnitude f, and then cos theta, right? So cos theta. Now you need to be careful. What is cosine theta? So for cosine theta, well, this is x, and then this is y, and then this is r. So cos theta is y over r. So cos theta is y over r, am I right? So I put this inside. So my fy is equals to this thing put inside and this thing put inside. Right, so I have now gm dm over r square, and then cos theta is y over r. So my y component is gmy dm over r to the power 3. So r to the power 3, so this is gmy dm. R to the power 3 is this thing to the power 3, so I got y square plus x square to the power 3 over 2. Okay, so oh yeah, I forgot, this should be the infinitesimal force. So this is the infinitesimal force. Because I'm only, so far I've only derived the force due to one piece from here. The total force is the sum of all the pieces. So the total force in the y direction is integrating everything dy. So I need to integrate gmy dm over y squared plus x squared to the power 3 over 2, right? And remember, dm was total mass over the total length dx. So I substitute this here. So my fy is equals to gmy. So I'm not integrating y, so I take it out. And then I got m over 2l, integrate x, and then y squared plus x squared to the power 3 over 2. Okay, and then you perform the integration. And then the rest of it is in the solution already, I think. Like yeah, so you get one, yes, so you get one from the other by differentiating. So this is the force way. So I don't know which one you are more comfortable with. Yeah, so both ways you need integration. If you do it this way, you directly get the force, so you don't need to differentiate anymore, but you need to be careful about this, right? So because the force has direction. This one only tell you the magnitude, right? So this part will give you the direction. Okay, any other question? Okay, what time is it now? 6. Okay, so if everyone is okay, let us actually, right, I want to do question 3 again, but using an alternative solution. Okay, because there's two ways to get the solution, right? For this one also, we either get the potential energy first and then get the force, or directly get the force. But now, since we're talking about potential energy kind of things, let me do question 3 again, and then I will use the force. Okay, so remember what was question 3 about. Question 3 is test. Yeah. Suddenly I want to check the recording. So question 3 is this one. We did this last time, right? So we did this last time, that particle of mass 3m and 1m, and then in the middle is small m, and then I want to find the equilibrium position, right? So yeah, so I have 3m, and then I have capital M here, and then I have another m here. So the distance from 3m to m is r. The distance from here to here is 1 minus r. So the total distance is 1. Okay, so I want to solve this again, but using an alternative solution. Okay, so my alternative solution is use potential energy. Okay, so what's my potential energy? So my my potential energy at m is is U. For potential energy between here to here is negative Gm 3m over r, and then potential energy is a scalar, right? So that's the good thing about potential energy. You don't need to worry about the direction, but the definition always includes the negative sign. So it's negative Gmm over r and negative Gm, and then this other m over this distance 1 minus r. So this is my potential energy of the system. Okay, so this is my potential energy, and then I want to find the equilibrium. So equilibrium, remember equilibrium means zero force. So to get the equilibrium, I need to differentiate this with respect to r. Okay, so I just need to differentiate r. So differentiate this with respect to r, I get a positive 3 Gmm over r square. Differentiating this, I get it becomes a plus over 1 minus r square, and then by the chain rule, differentiate this, I get an extra minus 1. Right, so if you simplify, right, you just get Gmm and then 3 over r square. Then this is a minus 1 minus r square. Okay, so for equilibrium, this term must be 0, right? So the derivative being 0 means this thing is 0. So 3 over r square minus 1 minus r square must be equals to 0. So from here we got the same equation that we got last time, right? So we can easily solve. So 1 minus r square is r square, so 1 minus 2r plus r square is equals to r square. So 3 minus 6r plus 3r square, r square. So I got 2r square minus 6r plus 3 is equals to 0, right? And then the general solution that we found was half 3 plus and minus the square root of 3, and then we reject the solution. So my final answer is half 3 minus square root 3. Okay, do you follow so far? Actually, yeah, you can just do the normal derivative. Yeah, it's the same. Right? It's the same. Okay. So so we have found the equilibrium position, and then the next thing is this equilibrium stable? Okay, so let's check the equilibrium stable. To check that the equilibrium stable, we need to see the second derivative. So yeah, so okay, let's use the normal differentiation because this my only variable is this, right? So my derivative is given by this. So my second derivative, let's see what happens here. So I got GMM, and then if I differentiate, right, I got negative 6 over R3. Differentiate this, I got plus 2 over 1 minus R3, and then by the chain rule, I got a negative 1. So both terms are negative, so I can take the negative sign out. 2 over 1 minus R to the power 3. So actually, right, to check the equilibrium, I want to see whether the second derivative at this position is positive or negative. So at this stage, you might be tempted to substitute R into here and then you try to simplify. But actually, I can give you a shortcut because, right, everybody here is already positive. Okay, so positive for the domain R to 1, which includes okay, so that means I don't need to substitute because it's everywhere this is positive, so minus sign. So the second derivative from here to here is always negative. Okay, so so this is negative, so that means du dr square is negative in a region including this part. So equilibrium is unstable, right? So negative derivative means that means this value is a local maximum, right? So it's a local maximum. So if you move it slightly away, it will continue to go further away. So it's not a restoring force. Okay, clear? Everyone clear so far? Okay, so if everyone is clear with this, let's do the next question. Yeah, let's do question 4. So I believe the rest of the question should be pretty straightforward, right? Question 4 is quite simple. At what distance above the surface of the Earth is the acceleration 0.98 instead of 9. So it's 10 times smaller, right? So if it's 10 times smaller, then how do you get the, what is the distance so that the is 10 times smaller? So this is question 4, right? So I have Earth, right? So the radius of the Earth is RE, but I want to get a new distance that is R away, right? And then at this position of mass m, what is the force? So at distance R from center of the Earth, so my force, the magnitude, we just need the magnitude, so it's gmm over r square is equals to mass times acceleration. So I can cancel the m. So my general formula for acceleration is gm over r square, right? So given an acceleration, I can calculate what is my necessary distance from here. Okay, so the mass of the Earth, no need to memorize, right? Is always given 5.972 times 10 to the 24 kg, and the radius of the Earth is 6.38 times 10 to the power 6 meters. So if I put these values inside, right, and then also I want my acceleration to be 0.98 meters per second, so I can calculate this. So this is 6.67 times 10 to the minus 11. The m is 5.972 times 10 to the 24 kg, and then the a is 0.98. So from here, right, we can calculate r square to be 4.0646 times 10 to the power 14, and taking the square root, you get 2.016 times 10 to the power 7 meters from the center of the Earth. So this is where you have to be careful. We don't want from center of the Earth. I want the distance from the Earth's surface. So from the Earth's surface is this value. So it's h, right? So that means the total R is h plus Re. So therefore the h is just R minus the Re, right? So the R is here, the Re is given here. So you take the difference, you get 1.378 times 10 to the power 7 meters from the surface of the Earth. Okay, any questions so far? Okay, yeah, so how's what yeah, so it's basically this lah, right? I just want to find the distance. Okay, any other question? So the next question I want to do, okay, so yeah, so let's do it slow. We have time, so let's do the next question slow. So question 5, right, is Jupiter's moon Io. It has active volcanoes, and this Jupiter moon, right, is famous for having volcano that shoot material very high up, so until 500 kilometers above the surface. So if Io have this mass and this radius, right, so we can measure this from observation. If we take the same volcano and put it on Earth, so how high up would it shoot from the Earth? Okay, so actually we can easily show a picture, right? Io volcano. The picture looks very nice. Yeah, so this is the Jupiter moon Io. So as you can see, right, the volcano can shoot very high until you can observe it from space. So this is the problem that we want to solve. Okay, so let's try to figure this out. Okay, so firstly, right, based on the information given, we are able to determine the initial velocity ejected from the volcano. So using this initial velocity, how high can you eject from the Earth? So that is the situation. So let us calculate the data on Io. So on Io, I don't know if it's called Io or Io. The mass of the moon Io is 8.94 times 10 to the 22 kg. The radius of this moon is 1815 times 10 to the power 3 meters. Okay. Yeah, yes, definitely. You can Google the mass and radius of the Earth also. Right? So now let us use conservation of energy. So conservation of energy. So the initial velocity is unknown, right? We don't know. So m is the mass of the material. But it doesn't matter because it's going to cancel anyway. Right? So m is the mass of the material ejected, and then the potential energy from the surface of Io is starting from the surface of Io. So by conservation of energy, it's going to end up at this energy at the end, so V2 square, and then minus GMI, and then m over the distance, so additional distance, so it's going to be higher up, so I want to plus HI. Okay, so HI is max height. So if the maximum height, that means when you reach the maximum height, the velocity will become 0. So this term is 0. Yeah, energy is easier, right? Because if you use force, it's difficult because your force is not a constant. So your acceleration is not a constant. So you need to integrate, then it's much harder to solve. Right? Yeah, it's more complicated. So you tried using linear motion, right? Is it? Yeah, so we use conservation of energy, and then we can cancel all this m over here. So we got half v1 square, and then I got gm over ri, and then this term is 0, so it's gone already. So this is gm I over ri plus the height. So I just need to determine my initial velocity. So I times 2 everywhere, so I take out the 2 and times 2 everywhere, and then v initial velocity is 2gm over ri minus 2gm. This is mass of io plus hi. Okay, so this is 2gm io 1 over ri minus ri plus hi. Okay, so yeah, so by now you should be able to determine the vi square, v initial square. So v initial square, just put in the numbers, 6.67 times 10 to the minus 11. The mass of io is 8.94 1022, and then the radius of io is 1815 times 10 to the power 3, and this is 1815 times 10 to the power 3 plus 500 kilometers, so 500 times 10 to the power 3. Okay, so it's a whole mass of numbers, but eventually if you calculate everything carefully, you can get the initial speed to be 1.19 times 10 to the power 3 meters per second. Okay, so this is the initial speed, the speed ejected from volcano. Okay, so this is the speed that is being ejected from the volcano. So next, we using this speed, if I take the same volcano and eject from Earth, how high can I go? Okay, so how high can I go? So for Earth, right, so I'm going to use this, and then the mass of the Earth, the R of the Earth is given. I'm lazy to write like so many things, right? You can check back just now. I want to calculate what is the height ejected from the Earth. Okay, so now I have the Earth. So I eject at v1, then what is the max height? So the final velocity is also 0, right? Max height. Why is it getting darker? Okay, so we're going to use the conservation of energy again, right? So again, conservation of energy. So at the position 1, at the starting point, my kinetic energy is half mv1 square. My potential energy is half gmm over the distance from the center is re, right? And by the time you reach the max height, I should have 0 kinetic energy. So this is 0. And then the at this distance, my potential energy now becomes Re plus He. Okay. So this is 0. Then, but this time, right, I know this number. This is the one that I want to calculate. So this is, so yeah, so we just need to solve it in this way. Let's simplify a bit. So firstly, let's cancel the m. And this term is 0. Let me take out the 2 and times 2 here, so it's easier to handle. So I got v1 square is equals to, bring this over, I got 2gm over re, and then minus 2gm over this plus this, right? And then I want to find this, so it's just math and algebra now. So I divide 2gm on both sides, and then I got 1 over re, and then this thing, and then this thing. So I can calculate re plus he is equals to 1 over this minus v1 square over 2gm. Right, so if I calculate everything over here, 1 over re, according to my calculator, is 1.567 times 10 to the minus 7. And then this last part is 1.777 times 10 to the minus 9. Okay, So I take the difference and then I inverse this. So if I inverse this, I got RE plus HE is equals to 654,841, and then minus RE, I got the height of the Earth. So the answer should be 74.8 kilometers. Okay. Yeah, any questions so far? Okay, so yeah, so it's time is almost finished. Yeah, no time to do any new question probably. Yeah, if not, we can still do. If still got any question you want to do, we can. There's time to do it on Wednesday. The quiz is due on Thursday, right? So, so on Wednesday we will continue on the physical pendulum. So let me remind everyone. For Wednesday class start at what was it? 4 p.m. right? 4 p.m. Yeah. So we delay by 1 hour, and also quiz 2 on Wednesday. That it was due on Thursday 12 p.m. Okay. Any question? So how come suddenly everyone is quiet for this part? The question not too difficult, right? For the gravity ones, except for the integration. So integration maybe must be careful a little bit, but for gravity, everything is just using the same equation over and over. Conservation of energy, Newton's law, all those kinds of things. Right? Okay. Why so strange? Am I online? Can you hear me? Wait. Yes. Okay, good. Double check. Yeah, so there's a quiz there, and then don't forget about the assignment, right? So okay, yes, let's open this. Download the file. So what is it? Let's see. How to open WebP? Can I open with GIMP? Galaxy Brain. Mechanics, calculus, thermophysics, class and notes. Why? So you're saying these two are the most difficult, is it? Wait, where's my Teams? Wait, what happened to me? Oh, somehow I couldn't rejoin linear algebra. Yeah, so when I was a student, linear algebra was the harder one for me. COVID 20, yeah. Yeah, I think it's because of COVID. Uh, yeah, so now suddenly I can see everything. Yeah, you got a lot of assignments, is it? That is the reason why mechanics, we only have 3 quiz. You can see my screen now. Okay, yeah, now you can see. Yeah, so I guess class is essentially over lah, so no need to see screen anymore. In fact, I should stop the recording.